Barbara talk about.
Thanks very much. So I borrowed the form of this title from the series of articles in the Notices of the American Math Society, which try to explain technical concepts in simpler language. And F-theory is something, the study of which involves a lot of theoretical physics and a lot of sophisticated mathematics. So I'm going to try to explain what it's about to a mixed audience of mathematicians and physicists, assuming that you don't know about the other field. So F-theory arose from string theory, and like many of the theories in modern theoretical physics, string theory is not a fully fleshed out theory. It's not something which mathematicians are particularly happy with, because a mathematician always wants to know what's the definition of your object. And string theory, like quantum field theory before it, is not something that we can give a mathematically precise definition to. But string theory is an approach to formulating quantum gravity theories. And it's an approach that's had a lot of success in describing quantum gravity theories. Since it's not a fully fleshed out theory, we don't know if it's a completely successful theory of quantum gravity. And even if it were the only theory that we as humans were able to write down as quantum gravity, that doesn't necessarily mean that it's the theory of quantum gravity that we live in, right? So this is a theorist's attempt to explain quantum features of gravity, which has been a big puzzle in theoretical physics for pretty close to 100 years at this point. I guess quantum theory isn't quite 100 years old, but we're getting there. So string theory is an approach to quantum gravity, and there was an early phase of string theory in which string theory was studied from the perspective of the string. So what's the string? The string is a 1 + 1 dimensional object in the theory. So it's called a string because its spatial dimension, it has one spatial dimension. So as opposed to a 0 + 1 dimensional object, which would only propagate in time and have no spatial dimensions. So there's a 1 + 1 dimensional string, and then in string theory, typically, we think of it as propagating in a background. And the backgrounds are generally taken to be supergravity backgrounds. So this, as the critics of string theory will tell you, is not an acceptable situation. We shouldn't have to say what the supergravity background is, because supergravity at the level of a true quantum gravity theory should only sort of emerge in some limit, but we don't know how to formulate it completely, so we'll sort of use this to try to study the properties of this theory even before having a complete formulation of it. So what's supergravity? Well, supersymmetry is an extension of the familiar Poincare symmetry of Minkowski space. So that's like the Euclidean group in ordinary space, where you have translations as well as rotations, except it's being done in Lorentz signature. So you do that in Lorentz signature, and you get a gravity theory, the symmetries of gravity theory in flat space-time. But then in supersymmetry, you extend that symmetry algebra, that Poincare symmetry algebra, to a superalgebra, and that constrains the theory further and actually lets you make more progress because you have quite a bit of a constraint. So supergravities were, it's embarrassing to speak of supergravity in front of one of the inventors of supergravity, but supergravities were developed and classified in the 1980s. And there are a number of them, but among the supergravity theories, the one that will be my focus today, is a particular one which is known as type 2b supergravity. So the fact that they've got names like type 2b means that there must be a few of them. There's only a small handful. And it's a 10-dimensional theory. So it's a gravity theory, so that means that it must contain a graviton. So now I'll try to speak of this theory in the language of quantum field theory, where I represent the constituents of the theory by certain fields. So graviton is a field that exists throughout space-time and which has the behavior that we expect of a field theoretic version of Einstein's theory of gravity, relativity. It has, in type 2b supergravity, it has a scalar field. So scalar fields are the simplest kind of field that you could make in a quantum field theory, namely it's just a function varying from point to point with some kind of Lagrangian or equation of motion governing its behavior. In spite of the fact that that's the simplest kind of field to write down, we didn't actually see one in nature until the Higgs field was observed not too long ago. And it also has a two-form it has a two-form field, and these fields together form one sector of the theory, which, from the string perspective, is known as the NS-NS sector of the string theory. That's just a name. So it's easier to give a general talk if I start with the 11-dimensional supergravity because it doesn't have too many fields. This one has a sort of plethora of fields. So in addition to this, there's another scalar field, another two-form field, and what's called a self-dual four-form field. And what that simply means is that it's a field whose field strength, which typically gets written as d phi, this is a local expression. The actual thing of relevance is a closed phi form rather than a 4 form, which is locally exact, but of course not globally exact. And the self-duality simply says that the Hodge star of that guy is equal to itself. So yes?
Is the graviton a form field?
The graviton is not a form field. It's a symmetric two-tensor field. So they all have sort of tensor descriptions. So there seems to be this extra collection of fields over here, which may be not a little surprising. This is called the RR sector in string theory. And then I have to say plus fermions, so I'm not going to try to explain what fermions are. Classical fermions are quite subtle and kind of hard to describe mathematically. Pardon?
The modern version of supergravity theory without fermions.
The modern version without fermions. Well, the fermions are really important, but in it, but to talk, yeah, it's without, yeah. That's supergravity without the super is what that is.
Only the leading term for the bosonic fields.
I'm just looking at the bosonic fields for today to discuss my supergravity theory. It's a little odd that there's this kind of duplication of fields, but it turns out that this type 2b supergravity theory has a symmetry, and there's an SL2R symmetry, which respects, well, the version one would like would be write down the fields, write down a Lagrangian, which exhibits this particular supersymmetry algebra. And that's not something that people know how to do. We don't have a complete Lagrangian because of this self-duality of the 4 form. We have the equations of motion, what you would get by varying a Lagrangian if you had one. So those are known. And even getting the super algebra to act is a little bit tricky. The super algebra only acts up to imposing equations of motion. So the whole thing is a little bit shaky. Nevertheless, on the solution space to the equations of motion, a so-called vacuum, you would see at least you would know the equations of motion for the fields, and you would see how the superalgebra acted. And in addition to this, to the super Poincare symmetry that we're imposing, there's an SL2R symmetry of this theory. And under that SL2R symmetry, the two scalars and the two forms each form two-dimensional representations. Okay, so this supergravity theory, as I say, I don't know exactly when it was written down, but it's from the 70s probably. You guys probably can tell me a date. It became one of the main species of string theory when string theory was first formulated. So we want strings propagating in the supergravity background. And the modification that you need to make for string theory, so there's some modifications. There are certain quantization conditions on some of these fields which aren't necessarily, they don't necessarily have to be imposed on the supergravity, but in particular, the Ramon-Ramon fields are periodic in some sense. And because of that periodicity, the symmetry in the quantum version is only SL2Z sitting inside of SL2R. So I have to say, for in the first era of string theory, when people started studying it in earnest, they were studying what's known as perturbative string theory, and this scalar field plays an interesting role. It tells you something about the interaction strength of the theory on the string. So this was being studied in some kind of perturbative expansion around a limiting value here, the so-called weakly coupled string value. And you can't really get perturbative string theory going unless you have a coupling of that kind. So how does string theory get in? Well, string theory is the string is closely related to this two-form field. Probably everybody remembers from elementary physics that if you have a charged particle and you want to measure the charge of the particle, you use Gauss's law, and you measure the flux of the electric field through a sphere surrounding the particle. There's also, what's the magnetic one called? I've forgotten the name. There's also the law for a magnetic source. So in Maxwell's theory, there are both electric and magnetic sources. And they can be viewed on an equal footing if you think of the electric source as being the integral of a field over this enclosing sphere, and the magnetic source, and sorry, this should be some kind of field over the enclosing sphere, and the magnetic source is really the integral over of the dual field. So you have these two kinds of sources associated to a given field. And of course, since we're going to integrate it, we want to be integrating something closed. So we integrate what are called field strengths. So we integrate a one-form field strength, a three-form field strength, or a self-dual five-form field strength in these corresponding situations. And in the second round of study of string theory, these type 2B theories got enhanced to 2B theories with branes, what are called D-branes, which are just sources, both electric and magnetic, for the Ramon-Ramon fields. So what I imagine is I take one of these fields from the Ramon-Ramon sector, I look at the field strength rather than the field itself, and now instead of just a point, I'll have some kind of extended object. So a point, by the way, in space-time still had time as a direction. So I'll have p plus 1 dimensions for my extended object, and that means I'll have 9 minus p dimensions, Riemannian dimensions, transverse to that object, and in there will be a sphere of dimension 8 minus p. So if I integrate either the field strength or its Hodge star over the appropriate dimensional sphere, I will find the possibility of electric and magnetic sources in a theory like this. And now that got coupled to strings in the sense that whereas the type 2b string theory originally was viewed as a theory of closed strings only, it turns out that these sources, so this is called a DP brane, turns out that these sources are places where the string can end. Moreover, a DP brane carries, or a collection of n DP branes together carry a UN or SUN, let me just call it SUN. Well, I don't want to get into the complication of whether the correct group is UN or SUN. Sorry, I want to use algebra. So it carries a UN or SUN gauge algebra in addition to the other things in the field, and those are gauge fields that are supported on the brane. So let me make a brief digression. You might have heard of brane world scenarios for our universe. In a brane world scenario, the gauge fields, the non-abelian gauge fields, the things that are responsible for all of the interesting physics, non-gravitational physics in our world, would be confined to sub-objects like DP branes, whereas the gravitational field would be allowed to go throughout the entire larger space-time, and that might explain the vast difference in scales between the gauge algebras of particle physics and the gravitational force. That's an idea that's been pursued, and there are various concrete models. I don't really know what the status of them is right at the moment. So the fact that there's a graviton in this theory means that I really should be specifying something about and this was implicit in a few things I said, I should be specifying a Lorentz signature metric throughout this entire space-time. So that's like a Riemannian metric, except I'm using signature 1, 9 in those cases. And there's a sort of a known asymptotic behavior for the metric near a DP brane. Okay, so the one interesting feature, which I haven't really used in this description, just sort of an observation, was the symmetry, the SL2R symmetry. And in fact, all of my description of D branes as belonging to the Ramon sector are kind of incompatible with the earlier observation that there was supposed to be this SL2R, or in string theory broken to SL2Z symmetry. What is it over here that corresponds to the objects over there? So let me now just state to you what F-theory is. I should say that this particular version of F-theory is pretty new. This is the third time that I've talked about it in some form, and even the first time it wasn't quite as fleshed out as it is now. And I'm writing a paper called What is F-Theory, but it isn't out yet. So what you're hearing is a very modern version of F-Theory, which very few people have heard yet. So F-Theory from this perspective is a quantum theory of gravity which, in some limit, reduces to type 2b, to SL2Z equivariant type 2b supergravity. So F-theory really wants to exploit this SL2Z symmetry in a serious way. And so saying that I'm going to impose SL2Z equivariance means that I can't really speak of objects individually that are acted upon by SL2Z, except under very special circumstances, as I'll mention. So for example, since the scalars are acted upon by SL2Z, I should really combine the scalars into a complex scalar. And if you normalize things properly, this complex scalar lives in the upper half plane. And this gets an SL2Z action, a very familiar one. Tau goes to A tau plus B over C tau plus D for A, B, C, D, a 2x2 integer matrix of determinant 1. So that's one of the features. And if you recall, I mentioned that the scalar field in the NS-NS sector of the type 2B string theory was supposed to measure the string interaction, but now I don't have that scalar field individually. I only have a kind of SL2Z orbit or multiplet of scalar fields. If I happen to be in a choice of vacuum where that scalar field is well-defined individually throughout space-time, I can then talk about a string coupling, but generally I won't be able to talk about one string coupling, but rather the couplings of the whole collection of strings at the same time. Similarly, the string was the magnetic source for the Ramon-Ramon two-form field, but now that's part of an SL2Z representation. The string was for the NS field. There's a related guy called electric source, thank you.
For the NS-NS2.
Pardon?
Electric source for the NS-NS2.
For the NS-NS2 form. Similarly, there's an electric source for the RR2 form called the D1 brane. And so those are kind of mixed up by the SL2Z action. And if I'm going to study SL2Z equivariant strings, except in the very special backgrounds where I'm able to identify those individually, I actually lose track of the strings. So F theory is not a string theory. Because it doesn't have a single string, and in particular doesn't have one that has a weak coupling description. There is an entire SL2Z multiplet of strings, but no single string. On the other hand, the thing that couples to the self-dual 4 form is the D3 brane. So F theory is a 3-brane theory, even though it's not a string theory. That viewpoint of F theory is something that's been studied off and on in the literature, maybe not so systematically. It's very closely related to the most interesting case of the so-called ADS-CFT correspondence, but in a case where you would want to look at D3 branes probing 7 branes as well as just out in empty space. It's something which ought to be pursued more, particularly in view of this discussion. So I need to tell you how...
A little bit previous versions of F theory.
Yes.
What is new here?
Well, you'll see, for example, the F theory, M theory duality only holds in special cases, as you'll see in a few minutes. So what I want to do is explain now some mathematical tools that will let me study SL2Z equivariant scalars in particular. So how to study.
The pair of scalar fields with the upper half plane. Is the first one the imaginary part? Is that the one that's positive?
Yes. Sorry.
The
upper half plane means the imaginary part is positive, so I better take that one to be the single valued one. The one that has the periodicity, which comes from the RR sector, should be the real part. So the real part has a built-in...
is from RR and the imaginary.
That's right.
NS.
That's right. And depending on your normalizations, you probably exponentiated the NS-NS field before putting it in. So how to study an SL2Z equivariant scalar? Well, I'm going to use 19th century work of Weierstrass. So on the one hand, you can write down Eisenstein series, which describe the SL2Z invariance for tau, except invariance is too strong. So there really aren't any interesting invariants if you insist on regular behavior, so no blowing up, no singularities. But there are covariants, things which transform in a predictable way under SL2Z. And there are Eisenstein series, which describe what are known as modular forms for SL2Z. So I'm going to consult my notes briefly so that I get all the normalizations correct. So if I have k at least 2, then there's an Eisenstein series, which I'll use this normalization with a Riemann zeta function factor, where I'll sum over all non-zero lattice points 1 over m tau plus n to the 2k. So you can see that that's going to throw off some kind of factor if I, generally speaking, for one of these modular forms, if I apply f to a tau plus b over c tau plus d, what I'm going to get is c tau plus d to the m times f of tau, and that'll be a modular form of weight m. And Eisenstein series are a nice way of writing down such modular forms. And let me point to a particular modular form which is going to play a role, which is delta says 12, but it's really 24, which is 4 minus a third E4 of tau cubed plus 27 times 2/27 E6 of tau cubed. And if there are number theorists in the room, I do apologize. The F-theory literature conventions about modular forms are well established, unchangeable, and not the same as in number theory. And it's actually my fault. Which is why an apology is appropriate. So what did Weierstrass do? Weierstrass wrote down a very cool function which depends on a complex variable together with a tau. So tau is going to be in the upper half plane. And what Weierstrass wanted was a doubly periodic function on the complex plane. So tau is going to be used as one of 2 generators of a rank 2 lattice that acts on the complex plane. So this guy is going to be a torus. This is T2 with a complex structure. And of course, identifying it that way means that I've chosen a particular basis of that torus. I could make a change of basis of the torus, and if I fix the orientation, a change of basis will exactly be an action by something from SL2Z. And then the tau, if you write it carefully, will undergo this typical fractional linear transformation. So if I succeed in writing some intrinsic expression for things of this sort, they will involve they should involve only things that are invariant or possibly covariant under the action of the modular group SL2Z. So Weierstrass did a very clever thing. He said, look, we can't, on a compact Riemann surface like C mod 1 comma tau, we can't possibly have a holomorphic function, but we could have a meromorphic function. That meromorphic function can't have a single pole, just a first order pole, because the sum of the residues of the poles, if you had a pole on the torus, you would get poles at every lattice point upstairs, and the sum of the residues would have to be 0, but if the residues are all the same, that's not possible. So we'll settle for a double pole, and he just wrote down, well, I learned this in undergraduate complex analysis. It's a really pretty argument to show the convergence of this thing, and you need this extra little factor to make the convergence work. You can't just naively sum these guys that you would like to. You have to subtract off the 1 over m tau plus n squared, and then somehow m and n, well, it doesn't matter. Here it was C and D, here it's m and n. I'm sorry about that. So you get a well-defined, it's absolutely convergent on compact subsets, meromorphic function on the complex plane minus all of these lattice points. And it has a double pole at each of the lattice points. So there's then a very beautiful algebraic trick. So what we want to do is let x be with my conventions, minus 1 over pi squared times this p function, and y be 1 over 2 pi I times the derivative of the p function with respect to z. And then there's an equation, which is y squared equals x cubed minus 1/3 times this Eisenstein series x plus 2/27 times this Eisenstein series. So this is the elliptic curve with modular parameter tau. And if you evaluate delta 24, you always get something not equal to 0. So that's sort of one direction in the connection between SO2Z quantities and something to do with algebra. In the other direction, I can recover tau by studying integrals of the following form. So I want to take an integral of dx divided by the square root of x cubed, and now I'm going to write it in slightly abstract form, x cubed plus fx plus g. So I want to take a ratio of two such integrals over appropriate paths gamma 2 and gamma 1. These are integrals of a complex variable, even though I'm calling it x. And I have to say something about, where I would have put branch cuts or something, where I would have put branch cuts in the complex plane to define the square root, and then where I choose my paths of integration. But the paths of integration are something like this, right? Typical thing of that sort. I don't really know which one is gamma 1 and gamma 2, or if I've got the orientation right, I think it's wrong. But something like that will reproduce tau mod the SL2Z transformation, where f is minus 1/3 E4 of tau, and g is 2/27 E6 of tau. So Weierstrass's basic result is that a pair of functions, f and g, a pair of numbers, f and g, will determine tau, an SL2Z ambiguous tau, by a trick like this of forming a ratio of integrals. And it's well defined up to a common scaling, which is actually compatible with this covariance of the Eisenstein series in an appropriate way. So if I have a pair up to a scaling like this, I get a tau, and if I have a tau, I get a pair up to scaling. This is what I now want to use to specify what's happening in F theory. So to say what the background is, I need to tell you an F and a G. And I want to exploit the fact that F and G have this common scaling behavior by saying that, so here's how I specify what's going on in F theory. I choose a line bundle, a complex valued bundle, a C-valued bundle, C-fibered bundle. Let me call it L, and I choose sections over my, now I have to have a name for my space-time, and my name is B, and I will call the space-time often the base. And the reason that I call it the base will emerge in a few minutes, where it's the base of a certain fibration, but typically F theory has not been presented only using the base, but here I really only want to use the base. So F will be a section of the square of this line bundle. G will be a section of the cube of this line bundle. So what is the line bundle business doing for me? The line bundle is letting me patch together different choices of F and G as functions on my space-time, utilizing the possible ambiguity from a scale factor lambda squared and lambda cubed. So I take that same scale factor lambda, I use it to build a bundle whose fiber is the complex numbers, and out of that, and then I choose sections F and G. And what I want to then study is the locus where delta of fg, which is defined to be 4f cubed plus 27g squared, is the same quantity that I just erased from this board. I'm sorry I erased it. It's the one which tells me whether there really was a tau. So I have to study that locus. And what I'm going to do is assign some kind of 7-brane type to, well, each portion of del equals 0, which is a manifold. So one of the things that I'm doing is giving a much more general formulation of F-theory backgrounds than has typically been given. And in particular, I'm not imposing any holomorphicity or anything of that sort. I'm just using the fact that F and G, two complex numbers, specify the tau. But then exactly what kind of smoothness behavior I require in order for this equation, which is really two equations, right? Because this is complex number, so I have to take real and imaginary parts of that equation. For that to impose at least generically something which is a codimension 2 submanifold of B, I'll have to put some kind of conditions on F and G, but I'm not going to say exactly what smoothness conditions I want, just to be adequate ones so that I have a situation like that. So there's a simple case, and
What dimension?
10.
That's the 10.
That's
9,1.
9,1. I think I would like F and G to be independent of time. I don't really know what time varying solutions are. I don't think I'm using it anyplace, but I get slightly nervous if I let them be time dependent.
So, they are interesting.
Pardon?
Time dependent back.
Absolutely, absolutely. Well, we just haven't studied those too much yet. Right, so I need to be able to tell you what else is happening near the zeros of delta. So metrically, there is a certain asymptotic behavior of the metric, which I'm not going to try to write down. I have to write a big table in a minute, and I don't want to take the time to write it down. But it's the same asymptotic behavior that people who study families of elliptic curves know very well. There is, and I also have to specify, so I must orient the normal bundle to the codimension 2 manifold components of delta equals 0. So I have to choose an orientation. But given that orientation, I then have a particular, so when I have one of these codimension 2 loci, I can take an oriented loop around it, and that determines an element in SL2Z up to conjugation. Which describes what multi-valued behavior of tau is being experienced as you go around that particular codimension 2 locus. And then, moreover, as I move transversely to that manifold component, there can be another conjugation. So let me call this one mu. Mu can also vary up to further conjugation in the parallel directions. So in other words, if I make a choice of generator here at a particular point, and then I move in parallel directions probably around some other components of this locus, and come back, I'll find a particular conjugate of the original one. So I need to keep track of those conjugations. So I mentioned that there was a group that was associated to a D7 brane. And in F-theory, we get to associate groups to all of these things. And let me just mention for people who know something about families of elliptic curves, that this assignment that I'm essentially making follows from Kodaira's work on one-parameter degenerations of elliptic curves. And at the very end of the talk, I'll say a little more exactly what the relationship is. But in Kodaira's work, you find that the one-parameter degenerations always contain some kind of ADE graph. And I'm about to associate a Lie algebra, and it's the same Lie algebra from the ADE. So it goes by means of a table. So I have to tell you the order of vanishing along my particular component. So I should give it a name. D is going to be the name of the component. So the order of vanishing along D of F, the order of vanishing along D of G, the order of vanishing along D of delta. And so those are those make sense as even in weak analytic categories of various kinds. The question is whether I can take an appropriate local equation for D and divide that local equation and still get a regular function. So if everything is holomorphic, things are great, but sometimes they're not. And given those choices, there is then an associated monodromy mu in SL2, and there is a gauge algebra, which is the analog of the UN or SUN that I was going to assign before. So so what are they? I can take, and I'm going to give the Kodaira notation for this guy. So there's the Kodaira notation IN, which has these guys order 0, this guy order n, this is 1n01, and this is SUN. There's a case which doesn't occur in Kodaira, but which has the opposite orientation. It's SUN, and let me just say that these are anti-D7 branes, which don't occur in the holomorphic context. Then there are other cases. If I have Kodaira type 2, that's 1, 1, 2, some clever order 3 matrix, and there's no group. And then for 3, this is SUN or SP, greatest integer in n over 2. There are two possibilities, and the difference depends on this issue about further conjugation, which I'm not really, don't have time to go into. 3 is 1, 2, 3, and it's an order 4 element, and it's an SU2, and so on, right? So there's this interesting list. All of the conjugacy classes of SL2Z are represented on this list, and you get not only the classical D7 branes and their close cousins, the anti-D7 branes, and orientifold planes. Those are all things which people worked out originally before F-theory, but you get some rather exotic things where there is an algebra to associate, there's a monodromy question, there's an extra parallel monodromy issue to be discussed. But there's a clear dictionary which says what group I'm supposed to assign to this thing. There is a Green-Schwarz term that goes in the action, which is related to this group. There is matter for this representation, which is associated to real codimension 4 loci in this picture. Everything we know about making a theory out of F-theory can be encoded into this language in which we don't compactify anything, but we express everything using the SL2Z equivariance. So let me just recapitulate. The main way that I used the SL2Z equivariance was to encode the SL2Z ambiguous scalar tau in terms of these two functions, two sections of line bundles F and G. And then I was able to read off lots of other interesting physical stuff, including what the behavior of various gauge algebras located in codimension 2 was supposed to be out of some known mathematics for this situation. Okay, so I promised that there would be some little more mathematics here. And so let me mention that I've partly specified the a gauge symmetry group in this thing by saying a non-abelian Lie algebra, but there's a further specification of the group. So let me just say what some further facts about these vacua are, and these require more sophisticated mathematics to even state mathematical tools. So, first of all, there is there's G, which is the gauge group, and I'm going to describe pi 1 of G as I never know if G is well, never mind. Pi 1 of the connected component of G, just to be safe, is going to be what's called the Mordell-Weil group of y squared equals x cubed plus fx plus g. So up until now, this equation showed up in Weierstrass's work, but y and x are not really part of my background. But I don't know. I suppose there are ways in which you could describe this group without invoking this equation. But what I really mean is it's the set of xy pairs. Oh. That's interesting. Okay, so so the previous time I gave this talk, instead of L, I had L tilde to the tensor 2. And the question from the audience made me think that I could get away with L instead of L tilde tensor 2, and right now I realize I can't. So this is sections of L tilde tensor 3 plus L tilde tensor 2, 2 and 3, with the property that this is satisfied identically. So in the most favorable case, which is the case where B is a complex manifold cross maybe a Minkowski spacetime, and F and G are holomorphic sections of a bundle, this is known to be a finitely generated abelian group. It's going to be an abelian group in any case, but the connection to pi 1 of the gauge group is probably requires it to be an abelian group, and I'm not sure exactly what hypotheses I need for it to be an abelian group. So anyway, under those circumstances, I can define this Mordell-Weil group, and if it has a free part, that means there's going to have to be a torus part of my Lie group. So my Lie group, or the connected component of the identity of my Lie group, looks like essentially S1 to the rank of this Mordell-Weil group, and then cross the various groups G sub D, which are the simply connected groups corresponding to the, I should have called this little g sub d, simply connected groups corresponding to those algebras. And then I should mod out by the torsion part of Mordell-Weil, which has, it's actually not hard to see how the torsion part acts here, and allows for non-simply connected groups to show up as non-abelian group factors in this situation.
Sections of the appropriate line bundles?
Yes, thank you.
Holomorphic? Or?
Well, that's where I get into a little trouble. I had F and G, which were sections, so this is an equation of sections. So I can certainly talk about the equation of sections. But unless I impose some holomorphicity here, I can't really invoke Mordell's theorem in any form and know that I've got a finitely generated abelian group. So that's why I had this digression about maybe I wanted holomorphic. Yeah, and X and Y should be holomorphic, of course, in this case. Well, I wrote the connected component. There's another question about the gauge group. And the pi 0 of G should be another interesting group associated to the y squared equals x cubed plus fx plus g. So again, in the holomorphic case, I really don't quite know how to formulate this in the non-holomorphic case. It's something called the Tate-Shafarevich group. Of y squared equals x cubed plus fx plus g. So the Tate-Shafarevich group is the number. So now I'm taking f and g to be essentially elements of some field, which is the field of meromorphic functions on the complex manifold part of B. And again, I hope and expect that there will be a way of formulating this even in the non-holomorphic part. And so what is the Tate-Shafarevich group? Well, it's something that is of great interest in number theory. You look for algebraic equations in two variables which have a solution set that's closely related to that of this so-called Weierstrass equation specified by f and g. And the specific relation is that you want the Jacobian curve, I'll just say some words and apologize for not explaining them. So I take other solutions, so functions of other variables equal to 0, and to that there is an associated so-called Jacobian curve. And if that Jacobian curve is equal to y squared equals x cubed plus fx plus g, then I consider that to be an element of the Tate-Shafarevich group. It's not obvious from that description that this is a group, but it turns out to be actually a group. And that's good because I'm trying to identify it with the group of components of the Lie group, and that is also supposed to be a group. So one of the facts that argues in favor of this identification is the identification of those two groups. Okay, so if I'm in this L equal L tensor, L tilde to the tensor 2 situation, there is an interesting duality which actually brings us to the way that F theory is usually presented.
Before you leave this,
Yes.
Was there, had some in some guys had Mordell-Weil and Tate-Shafarevich showed up in the physics, or is this the first time they've been associated with F theory?
No. I associated these to F theory about 15 years ago. The thing that I'm
physics description, or do they correspond to something physical in the theory?
The pi 1 and pi 0 of the gauge group.
But do those give you fields, or?
So right. So how do we recognize? Let me focus on this one first. How do I recognize pi 1 of the gauge group? The way I recognize pi 1 of the gauge group is if the gauge group is not simply connected, then I will, let me just talk about the non-abelian part for a second. If the gauge group is not simply connected, then I will see a deficit in the representations which occur. Mm-hmm. So missing representations should somehow correspond to a particular finite order element of the pi 1 of the gauge group. I did not tell you how to get the matter representations out of the geometry, but there is a clear dictionary between a restriction on the matter representations and a particular Mordell-Weil group, Mordell-Weil lattice, and that's essentially how you establish that this is what pi 1 had to be. So this puts restrictions on the representation theory. Pi 0 shows up when you compactify down one dimension, which I'm about to do. And in 6 minutes, I can hopefully tell you a little more about why it's Tate-Shafarevich. OK, so what I want to do now is take B to have a special form. I want it to be S1 cross B hat. And as is often done so this is called compactifying the theory on S1, but since I'm not separating out a compact and non-compact part, I'm simply going to specify that I'll now look only at spacetimes of a particular form, and this should actually be this should be the sort of this should be a flat circle, if I can call it that. I just want the ordinary metric on the circle. So one of the ways that people have made progress in studying string theories and their cousins, such as F theory, is to find situations in which a particular space-time configuration in one of the theories will give the isomorphic physical theory, at least once you take care of extra features having to do with the compactification, to some other theory. So these are often known as dualities in the theories. And what I want to talk about is what's called FM duality. So I want to relate the F theory on that space to a different quantum theory called M theory. M theory is related to 11-dimensional supergravity. And 11-dimensional supergravity is even easier than 10 dimensions because all it has is a graviton in the bosonic sector is a graviton and a 3-form. So I don't have to write down all those fields that I did in the 2B case. And the proposal is that you take M theory on the solution set to y squared equals x cubed plus fx plus g, fibered over, I don't want to call it cross, b hat. So I have to make sure that none of the data, the f and the g, the f and the g don't depend on the S1 direction. But then once that's true, I get a family of solutions to this. And then I want to do geometry, so I'm going to allow myself to put a tilde here, which will be with appropriate modified metric. So there are lots of possible metrics that I might now choose on that space. To discuss M theory, I need a metric, so I have to consider one of the pieces of data to study when I do this compactification to be that choice of metric. So let's see. And so what I want to say is that this guy corresponds to the limit here when the area of y squared equals x cubed plus fx plus g goes to 0. So I choose my family of metrics, but now to recover the F theory limit, I should take the area to go to 0. And here I want to take a limit where the radius of the circle goes to 0. No, sorry. I do not want to specify the radius here. Sorry. Any of these F theory vacua correspond to something over here. OK, so this is the way that F theory has traditionally been presented. We study spaces of this nature. And if F and G have been chosen to be sections of holomorphic bundles, then this is actually going to be some kind of algebraic variety, has a nice algebraic equation. The form of the equation tells me that it's fibered by elliptic curves over B hat in some way. And then this Mordell-Weil group and Tate-Shafarevich group are standard geometric things that you might consider about that fibration. Let me just mention the Tate-Shafarevich story. So here's a question you can ask. And the question from the physics side and from the math side are slightly different, but they're essentially the same thing. From the physics side, you can ask how many discrete gauge choices are there Because to build spaces like that, I should be allowed to make a discrete gauge choice as I go around the circle. So how many discrete gauge choices are there to put on the circle? And the answer is the component group of the gauge group. So if I've got a disconnected gauge group, then I will have the possibility of exciting those discrete degrees of freedom as I go around the circle. The math question is, how many of these manifolds, I'm going to call them Calabi-Yau manifolds, elliptic Calabi-Yau manifolds, or maybe I'll just call them elliptic manifolds, have the same area of curve goes to 0 limit. Well, when the area of the curve goes to 0, the only information that you're left with to describe the manifold is this equation, y squared equals x cubed plus fx plus g. The metric information has gone away. Now, there's a Jacobian construction in this broader context, so that if I have something fibered by genus 1 curves, there's a so-called relative Jacobian fibration. And again, the only information that you'll retain in this area goes to 0 limit will be what were the f and g, the Weierstrass coefficients of the Jacobian fibration. So the answer here in this nice number theory situation is given by this Tate-Shafarevich group. So this is why I identify them. I get a number of choices of types of Calabi-Yau manifold, elliptic Calabi-Yau manifold, a finite number of choices after I compactify in a circle, and that corresponds to the discrete gauge choices that I might have made before I compactify on the circle. Okay, well, the whole thing was maybe more technical than I had intended. I hope I may have communicated parts of it to some of you, and I thank you for your attention.
Questions?
Yes?
Yeah, so it's a long-standing question I have. Maybe it's silly, but Ref theory focuses on the scalar field. But there's also, of course, the two forms,
Right,
which are formal SL2 representation.
absolutely.
And so wouldn't a more complete formulation also have some sort of bundle for those?
Absolutely. So I didn't have time to say that. So the earliest, so there's a very pioneering paper that Daniel Park, Mike Douglas, and Christian Schnell, all local here, wrote last winter exactly about this issue. So they were worried about the K3 case, but their techniques extend immediately to arbitrary cases. And one of the reasons I was focused on the monodromy is that monodromy produces for you a natural Z2 bundle with monodromy over the complement of delta equals 0. And that is a bundle underlying the quantized two-form spaces that we want. So it's completely built into this formalism. All I have to do is specify the f and the g, and then the monodromy tells me what the compatibility condition is for the bundle. What they analyzed closely was under what conditions will you get sections of that kind of varying bundle so that you actually have some reasonable two-form in the theory instead of just having a multiplet of two forms. And they found answers which helped explain the discrepancy between the brain picture of K3s that has 24/7 brains and therefore should have a U1 to the 24 billion group, and the fact that it's actually only U1 to the 20. So they explained the discrepancy in a very, very elegant way in that paper. So yeah, I should have mentioned that paper, together with some work that's an ongoing collaboration with two papers so far of Grassi, Halvorsen, and Shanison, studying much more from this point of view, F theory, instead of always worrying about the Calabi-Yau, where I should have mentioned that this choice of metric introduces lots of extra parameters which you don't really need for F theory. And so their point of view was, if I deform F and G slightly, I should be able to understand everything I need to know about F theory. And those are two of the big ingredients that led me to this point of view.
Any questions? Well, let's thank you again.